All right, I'll get started. Welcome, everybody. Thank you all for coming. My name is Michael Park. I'm a software engineer at Facebook, and I work on C++ libraries and standardization efforts for Facebook. So this talk is going to be a sneak peek into a specific paper that proposes a language feature called pattern matching to C++23. I say a sneak peek, but I'm actually going to throw a lot of information at you, so we're going to go a little bit quick. So the specific paper number is P1371R1. For those of you who don't know, you can use wg21.link/P1371R1 to get access to the paper. So these are the co-authors. The folks are from Facebook and Bloomberg. So myself from Facebook, Sergey, David, and Dan, who is in the room, are Bloomberg folks. And so this has been a collaborative effort between Facebook and Bloomberg. This talk has two goals in mind. One is to help you build an intuition as to what pattern matching is, how it works, and how it can help you simplify your code. And second is to gather feedback. Because ultimately, we want the feature to be awesome. We want to share early as to what the early design phase is and get feedback as to what people like, what people don't like. And we've gone through some of these iteration phases already. So by show of hands, how many people are already familiar with pattern matching from other languages, from Haskell, Swift, Scala, what have you? Okay, this is about, I would say, more than half the room. So maybe you guys are already convinced, but for those of you who didn't raise your hands, let's go through some motivations. So the point is that we have these two extremely common and simple tasks that we perform in programming on a daily basis. One is selection, and the other is decomposition. These words might sound fancy, but selection just means performing different actions depending on a value. You already know this from examples like switch and if. And decomposition is just about retrieving components out of a value. So we typically do this through a member access or with structured bindings, which was introduced in C++17 to help with this problem. And these two things should be simple. And let's see where we are today. So with selection, we have two selection statements in the language. One is switch, and the other is if. So let's take a look. So first, switch, obviously, is the first thing that you would reach for when you're looking for something to do a multi-branch testing, right? And soon after you start using it, I'm sure all of you know that you can't match a string with a switch because it only supports integrals. Except that it doesn't only support integrals, it only supports a single integral. So even if you just had two integers, x and y, and you wanted to test both of them are 0, you couldn't say switch x comma y and then case 0 comma 0. You'd have to actually nest switches to get what you want. And so we would like to be able to do better. So the other side is an if-else statement. Here we have a classic shaped class hierarchy, which is a polymorphic type, circle and rectangle, which inherit from shape, and a naive implementation of getArea that performs dynamic cast to check the elements that we're the derived class that we're looking for. So most people would look at this example and say, don't do that. And the blame typically goes to dynamic cast. And the point I would like to make is that, I would like to argue is that it's actually not dynamic cast's fault here. And the reason I say that is because dynamic cast is already slower than a virtual function call. But let's assume that dynamic cast is only as expensive as a virtual function call. Even if that were the case, this would still be double the cost, right, potentially. And if there are n of these, it would be n times the cost. And the reason for that is actually not dynamic cast's fault because the if-else, the control structure used here is just way too flexible for the compiler to be able to reason through all of these conditions, these arbitrary Boolean expressions, and to know that we can actually consolidate these dynamic casts into a single virtual dispatch. So inherently, what we're looking at is a structural association. So what I mean by that is if you look at the switch example, we have an int value, and we have case C1 and C2. Okay, and C1 and C2 are arbitrary expressions. Now, even without expanding C1 and C2, I can tell that the result of the values of those expressions will be compared against value, right? On the other side, we have if, and the B1 and B2 here are arbitrary Boolean expressions. And without expanding B1 and B2 and analyzing the Boolean expression, we have no idea whether those conditions have anything to do with value. Is that clear? Seeing some nods? Okay. So those are two selection statements we have, and what we want to strike is a balance in between these. So we want the structural association of switch, but we don't want the limitations of switch. So we want to essentially, from one perspective, we want to improve, it would be a switch on stereos, if you will, and from the other perspective would be a structured if-else chain. So we're trying to strike a balance in the middle. An important case for me to cover here is std_visit and std_variant. So many of you may have, some of you, or maybe many of you, may have seen this article which states that std_visit is everything wrong with modern C++. So just so I have a feel of the room, how many people are familiar with std_variant added in C++ 17? Okay, so I think most of you. Std_variant basically allows you to hold one of n elements, and you can use std_visit to basically pull out the value that is stored inside that variant. And it is very complicated. So I'm not going to go through it in a lot of detail, but just to convince you that it's difficult, let's take a look. So this would be the most basic use of it. We first construct a variant of bool int string, and then we set up a visitor, which is a struct with an operator, callable operator that handles each of the cases. Okay, and at the end, we're going to do std_visit of visitor onto the variant that we have. Now, a lot of people are bothered by the fact that we have to define the cases out of line. And so ultimately, they want to write something like this. And so we have visit of overload of these lambdas, and overload there is creating an overload set. And this would be a slight improvement, and already it gets very complicated. So here, this is the overload helper. This involves variadic templates, variadic multiple inheritance, variadic using, which is only added in C++ 17. So if you try to implement this before that, it would be a lot more complicated. We have class template argument deduction and deduction guides in order to achieve this. The code is short, but the amount of C++ knowledge you need to understand this is a lot. Let's move forward. So here is this. By the way, these are examples that I pulled off from CPP reference. So I'm not just like making stuff up here. Okay. So this example is a way to use a generic lambda to visit an arbitrary variant, and the way we're going about handling the cases is by using a context per if to analyze the types explicitly. And at the end here, we have this always false thing. Again, I don't even want to explain this, but it involves dependent types and the instantiation of templates so that we can get exhaustiveness checking if you happen to not handle a case that we're supposed to be handled. So that involves introducing this always false helper, and I don't want to explain any of this, right? I want people to just use a variant which can hold one of n things and just take stuff out and go do your job, right? Like I don't want to explain all of this stuff. So again, we want to improve on std_visit and the usability of it, basically. Now, the other side of it I mentioned is decomposition. And there's not much to say here aside from the fact that it happens all the time. So typically, in this example, where we're doing naive selection, we're going to do member access to get the pieces out. After we select the item that we want, we're mostly going to access elements out of that to do stuff, right? With structured bindings, you can change it a little bit, and so if you happen to refer to the members quite a bit, then you could shorten the syntax. But this is just for completeness in this area. Now, if we put these together, then we get something it gets very complicated. So let's do our setup. So we have this message class, a message type, which is going to be a variant of 4 commands: quit, move, write, and change color. These are our commands. They have associated data, and we're going to basically just visit them, right? So we're going to say visit of overload of all of this stuff. And so what we're seeing when we see something like this is we're first selecting across the vertical axis, and then we decompose on the horizontal axis. And so we're doing that for other types, but for the other cases as well, but I'm showing it for this particular case. So if we were to, and this might not actually look too bad, right? You kind of know what's going on here, and it's like a little bit of boilerplate, but whatever. But once we start nesting it, it becomes a lot more hairy. So let's say the change color command, we replace the data members to actually abstract it out to a color class. So that variant is going to be an RGB scheme or an HSV scheme. I have no idea what that means. Doesn't matter for this example. So we're gonna store this color instead, okay? And then I want to select across the top level. I want to grab the color out of the change color argument, and I can't even fit this on the single slide anymore, right? And then we're gonna visit again. So this is selection, composition, decomposition. We select again, and then we have to decompose again. And so it adds this level of nesting that makes code very difficult for us to read. So what's the alternative? So let's look at what Rust does in this example. So this example is actually pulled out from this URL. Assume the exact same data structures that we've set up so far, and this is what we end up writing. So we're selecting on the vertical axis still. We decompose horizontally, we select again, and we decompose again. Right? And so all of these things are happening, but it's happening in a very compact way where the construction of the value looks very close to the construction of the pattern. And so you can actually, without me having to explain this example, you can probably guess what it does. Okay, so the takeaways for motivation generally is that selection and decomposition are extremely common operations that should be simple. We want a general selection mechanism between switch and if-else. Selection and decomposition very often nest, and nested selection and decomposition lead to a lot of indentation, which generally I correspond with program complexity. So what is pattern matching? So this quote is from the Haskell wiki, and so obviously it's correct. So it says that in pattern matching, we attempt to match values against patterns, and if so desired, bind variables to successful matches. Okay, so I have this information card up here with bold value italicized pattern and underlined variable with color codings so that we can keep track of what components are referring to, correspond to what. So let's go back to Rust for a minute. Quick example, we have this point class, which is very simple. We have an x and y. We're going to create an instance of that point, and we're going to match on it. And what we're doing is the first pattern will match any x and a 0 for y. And the second pattern, which will not match because we have y equals 7, right? And the second pattern will match because x is 0 and y can be anything. And then the y there will bind the value that's stored inside point, and when we print it, we get y-axis 7. Okay, I don't see any frowns, so I'll move on. So in C++, we'll probably have to write something like this, right? We would, rather than being able to describe the value that we want to see, we would actually have to perform imperative actions to see, to pull out the conditions that we actually want to see, right? And so the color coding here is basically where values, patterns, and variables lie. So from this perspective, declarative pattern matching can be seen as a declarative alternative to manually testing values with conditionals and extracting the desired components. So let's take a closer look at a pattern. So this was a pattern that we matched a couple of slides ago. And there are two things that are embedded in this pattern. One is the testing portion, right? The x:0 is actually testing for point.x equals 0. And the second part is extraction. So rather than doing point.y, we're saying just bind, like I'll give you a name, make that thing the thing that I want, right? And so it's a very compact way of compact description of the actions that we want to perform. And this might actually remind you of regular expressions. So if we look at a regular expression like this, there will be a first component, which is a test component, which matches letters followed by digits. And the second component will be the extract portion, which extracts digits out of these the string that we're matching. So at the core of patterns, a pattern matches and or binds. So it could match and not bind anything. It could always match and only bind, or it could try to match and bind. And by match, I mean it could try to match and fail, right? And so if it always matches, then that's not going to be matching that I'm talking about. Let's go back to the select plus decompose example. So if we color code the parts that I think are associated in this example, I think this is where the colors fall. So we can see the message is all the way down here. We have the patterns in the middle, the variables that I introduced, and blah, 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 right? So with the proposal, where we want to go, oh, sorry. Here's the thing that I want you to, whoa. Sorry, wait a minute. There we go. Okay, so what I want you to focus on here is that there's this change color variable introduced, and then we use it immediately. And once we use it, we don't use it anymore. And we're looking at this change color type and the structured bindings decomposition, and we have this like baton passing that happens that doesn't really need to happen. And so when we collapse that, we end up with something like this. So you can see from the change color type, I'm talking about this right here, from the change color type to the structured bindings example, there's no giving it a name just to pass a baton along anymore. And so we get much more compact code. So how does it collapse for this example? So we have these kind of color scheme, and all of this is going to collapse. So let's look at it. So here's the RGB structured bindings. There's the RGB type. There's the color decomposition and the change color. Okay? And we're going to describe all of that in a single pattern. Okay? All right. So the key idea here in terms of patterns and pattern matching, the value that, well, okay, I'm going to talk about values. The benefit that you get from using patterns is that patterns and values are both built via composition. So what I mean is in C++ or most other languages, we build these values through composition. So we may have some kind of integral. We might put that into a pair. We might put that into a struct. We might put that on the other side of a pointer or whatever. All of these compose, right? And then right now what we're doing is we're working inside out while we build it, and then when we inspect it, we're working outside in. And so because patterns allow you to partially build values inside out, you end up building values inside out and then inspecting inside out again. And so if you think about the cognitive load involved in doing those operations in your head, the analogy I like to make is that singing the alphabet song forwards twice is significantly easier than singing it forwards and then backwards. Okay? And so I think that this will help you sleep better, basically. I would like to sleep better myself. Okay. So I think we know roughly what pattern matching is about and what patterns do. Let's get a little more specific. Here's a structure of the proposal that we actually have in the paper. The first one is statement form. And so if you ignore the optional components of this syntax, we end up, I'll give you an example in a minute, but just to walk through it. We have inspect, we have the value that we're inspecting. We have a sequence of patterns with corresponding statements, and each pattern has a matching semantics, right? And so if that pattern matches, then it's going to execute the statement that is corresponding to that pattern. Okay? Pretty straightforward. And this is going to occur on a first match basis. So here's a simple example. The thing that we couldn't do with switch, we match some string, we give it string literals, and the first one that matches will execute the corresponding statement. And note here that there's no break. And so with pattern matching, we don't have fall throughs. and that'll be a good thing for everyone. Second one is an expression form. Now, we can kind of get this by wrapping these statements in a lambda, but all of that gets very hairy, and having an expression form would be very very useful for a lot of cases that we'll see later as well. So how this works is you say inspect of some value, optional trailing return type. We'll look at why that might be needed. We have patterns corresponding to expressions, and the first pattern that matches will return, basically produce the expression on the right hand side. So here's a simple example. We inspect it on some x is an int, let's say, and we produce a string as an expression, right? And then we can actually capture the result of this inspect because it's an expression form, okay? Now, if we change the types of the expressions, then we have a problem, right? Because this is similar to having multiple returns in a lambda. And so if you have multiple returns in a lambda and you have deduced return type and they don't match, then the compiler will say, try again, right? And so in those cases, you actually need to specify a return type so that the result can convert to it. And so in this case, the first 0, string literal, will actually convert to a std string, and the result of that whole expression will be a std string. I think that's pretty intuitive, right? Now, there are these guard pieces here, right, which are a bit mysterious, so let's look at that. So here's a pattern guard. I haven't quite introduced the structured bindings pattern, but I think you kind of get what that would do based on how structured bindings work. So we're going to match some pair here. Oh no. We should be inspecting something that's not called X. This is sorry. So let's say we're matching some S, I don't know, and we're gonna unpack it into X and Y, and if we wanted those two things to be the same, then we can say if X equal Y on the right hand side there. And so the semantics of this is if the pattern matches and the guard passes, then the statement is executed. If either of those fail, then it'll fall through to the next case. Okay?
Couldn't that X just be a pair, and is there any concern about names, scope names shadowing? Like, is there any restrictions on names? Like, could it actually be X?
Yeah, so the question is, the terrible thing I did here, is it actually allowed, and would it work? How would it work? It would actually work as we expect, in that, like when we say X equal Y inside the if, it would refer to the binding as opposed to the thing that we're matching. So it does shadow properly, but yeah. Okay, now those are new things that are fancy and exciting, to me at least. Now, the other thing that we need to consider though is how all of this fits into the rest of the language, right? And we want this whole feature to be cohesive. And so we need to look at how this pattern matching stuff and patterns in general fit back into existing declaration forms. And so does this work? And if it does, what does it mean? We need to define all these things. So what I'm going to say for now is that simply put, we can put patterns that cannot fail here. Okay? That's it. You know it's okay. Okay, let's go through the patterns now. So overview of patterns. So quick disclaimer here. Obviously, none of this is in the working draft or anything. It's targeted for C++ 23. Details subject to change. But some of these have gotten pretty good feedback, and so some of them will stay around. But you know, don't be too tied down to the syntax too much. Focus more on the semantics of where we're going. So let's look at primary patterns. The first one is the wildcard pattern. This one was and is quite difficult because we really want this to be spelt single underscore. But this is the working status of the wildcard. So it's a double underscore. You can repeat them how many ever times you like. They don't actually introduce an identifier, so you don't have multiple declaration issues or anything like that. And if we were to right? So if we were to port that back to the declaration form, then we have what's on the right, where we can ignore stuff in structured bindings, and we can have lock guards that actually don't have arbitrary names and nice things, except the name. Oh, by the way, if you have questions, if you can go to the mic, that would be helpful for me. I would come back to it. Okay, so let me cover one more, and then I'll answer the question. So the next one is an identifier pattern, where we just put an identifier, and it introduces a binding. And so here, we're matching on some value, and we're giving a name X, and then we're going to print it. Right? Nothing exciting. The exciting part, actually, more so, is that how this fits back into the declaration form. Right? We can look at the auto X equal value as a declaration form of pattern matching where it's just an identifier pattern. Okay. Did you want to ask a question?
Yeah, just a quick question.
Yep.
In the previous slide,
Yep.
the wildcard, since you're using a double underscore and considering a single underscore, any reason you just wouldn't use a classic splat or asterisk for the wildcard? Thank you.
Asterisk. Yeah, so imagine what would happen for this example where we say auto star equals value. Is that a pointer? Is that a missing name? What's going on, right? I think when you put things together in that context, it gets, especially in a function parameter where you can actually omit the name. If you see auto star, that might be a pointer. That is a pointer. So that's the problem. Okay. I think we're all right. So next one is the expression pattern, where we can put any constant expression into a pattern matching context and match against the value. Okay, so the first example is matching some integer again with 0 and 1, very simple. The second one is matching an enum with the corresponding enum values. So this works for the most part, except identifier. So this is the core of the difficulty in introducing pattern matching as far as I can see it. So why? The issue is identifier and ID expression are the same thing. So we need to figure out what we mean, right? When we see X, is it introducing a new name, or is that trying to refer to an existing variable? So a concrete example of this would be there's some static constant expert int X, and I say match this value with X. What does that mean? What does this mean? Is this going to match or not, basically, right? So this is the core of the problem. So what we're proposing is for us to have two modes. One called bind mode, and the other one called expr mode. And so the meaning of those things would be that in bind mode, identifiers are interpreted as identifier patterns, and in expr mode, identifiers are interpreted as ID expressions. So you can see on the left-hand side, we say bind X, for example, and that would introduce a new variable X. On the right, we have the same enum example, except we say expr of, oh, sorry, not the same enum example. This is a different one because it's not scoped. So before, this was not a problem because color : red is not an identifier, right? So we get away with it. However, if we have an unscoped enum, then now it's an identifier. And so we need to figure out what it means. How do we make it refer to the values of the enum? And so in this case, we're saying expr of the identifiers refer to those values. Okay, so here's an observation. Look at existing declarations, right? Existing declarations like variable declarations and structured binding declarations are by default, the identifiers that get introduced in those patterns are by default identifier patterns, right? They introduce new names. Whereas if we look at the switch example, identifiers are by default ID expressions, right? So there's this existing world that we want to try to be cohesive with. So here's the idea. We rename bind pattern to bind mode with let pattern, and we rename expr to case. So on the left, and the top level is implicit, And so that's how we get away with auto X and auto structured bindings to be identifiers by default, because it's let by default, okay? And so here we're saying let X, where X introduces a new name, and on the right we say case of some pattern, where pattern in this case is an identifier, and that's going to be interpreted as an ID expression. People see that? Okay, so if we put them together, then we end up with something like this. So we have constants 0 and 1, and we have a arbitrary, kind of a naive example of a pair of int and pair of int int. And we can say case of 0, let x, y. And so these things can nest, and the most recent ancestor basically wins. It basically sets the context. And so 0 here would be the ID expression that refers to the constant, and x and y's that are inside let would be introduced new variables. Yeah.
Why don't you want to mention the p in each production? Then that would sort of disambiguate this problem.
I didn't understand. Why don't we repeat the p?
Well, if you use p here, you can say.
Where do you mean by here?
Well, in the first case, for example.
In the first case, instead of.
Right.
What do you mean? P where?
P. If the p is used in the statement, in the case statement, then
okay.
You can tell which you mean, whether you mean a value or extract something.
You're saying instead of let x, y, you could say p dot first?
Yeah, p dot first, x, y,
Oh, you're asking why we can't, why we wouldn't just access the value so that they end up not becoming identifiers? Is that what you mean?
No, you could still have new identifiers, but if you use p in this example,
yeah.
Then
you mean on the right hand side? If we
yeah.
just use p.x and stuff.
Yeah.
Yeah. So this is a simple example, but once you get more nesting into your patterns and stuff, you won't necessarily have access to that as simply as in this example. So in this example, it's just one level down, but you might be somewhere deeper in the pattern, and then you could, rather than, if you didn't bind names when you're deep in a pattern, you would have to get the value on the right-hand side and access all the way down in order to get those pieces out. Did you have a question, Richard?
P in this case was an expression and return that. There's no name to use. You wouldn't have P, and it's just an expression.
Oh, right. Okay, yeah, thank you. So Richard's comment was that if you didn't actually save P and put the right here, if this expression, the ... went directly into the inspect, then you wouldn't necessarily have a name to refer to on the right-hand side. So yeah, thank you for that. That's helpful. Okay, let's keep going. Compound patterns. So I don't think I need to explain much here, but I'll just show it for posterity. So basically, it's structured bindings, as you know today, put into a pattern. Not much going on, except that inside those patterns, inside those square brackets, you can put patterns, right? So today you can only put identifiers in there, but ideally you'd be able to put patterns in there, arbitrary patterns in there. And the semantics are just that it matches, it's consistent with structured bindings. So I don't really want to get into explaining that part just yet. Okay, the next part is new. So this is using designated initializer syntax, but on the other side. And so rather than being forced to give names to every part of the struct or tuple that you're unpacking, you can actually, in the case of a struct, you can actually pick and choose the components that you want and leave the rest out. Right? So in this example, we have this player class with hit points and coins, and the first pattern, for example, just cares if the hit points field is 1 and doesn't care what coins is. Okay, and I think the rest of it is pretty self-explanatory. But this is very useful, and I think it's very consistent with how designated initializer construction works today. So that's pretty cool. Okay, let's move forward. Alternative pattern, I mentioned one of the motivations was to improve std_visit. And so the example here is that we have a variant of int float, and this is what you would write to inspect the components, inspect the alternatives rather. Okay. Now, it's important to note that this works, the way this actually works is very similar to std_visit. And so this slide is here just to show you that we're not calling getIf, right? Because if we were to do that, then calling getIf int on this on this variant here would be a compiler error because it's ambiguous which one we're talking about. And so, like std_visit, where you can pass a visitor with an int handler, and both of those alternatives would invoke the same handler, same thing happens here. Both ints, even though they're different, will actually be handled by the same handler. What if we want to separate them? Well, we can actually specify a constant expression in there to, and in this case, we would actually just match for the v.index, right? And we would dispatch to the correct handler corresponding to the v.index. Basically like a switch, right? But we actually do the matching and the grabbing of the value and the unpacking for you, basically. Okay, and going forward with the std_visit example, you can also put auto in here, which would mean that you match anything. And so this is kind of a contrived example, but you can have other cases above this auto and have this auto be the default. Okay, the next one is to allow putting a concept in there. And so in this case, we would have this bool, char, int, float, and string. And if you put integral concept into one of the cases, then you would handle bool, char, int, float, and the auto would handle the string case. The alternative pattern actually extends much further. We have an any-like support where this would call, this would subsequently call anycast on the A, and it would bind to the correct handler. But this one doesn't support auto and concepts and stuff because we don't have that much we don't have enough information for that. Now, lastly, but not least, polymorphic types. The get area example that I had earlier with the if-else can actually be improved to be written like this. So this is the first instance of the expression pattern that I've shown here, where you would inspect the shape, the two cases, get the pieces out, and then you just write the expression and that you return the entire thing.
And what happens if you put shape in there as a type?
Put shape in there as a type.
Yeah. So
okay. I'm going to defer that question to what happens if you dynamic cast a shape to a shape. The answer to that will be the answer to your question. I don't remember what the answer is for that. Yeah, I really don't remember. Sorry. Okay, let's move forward. The next one I want to share with you is the reference pattern. So the syntax is star bang or star question mark. And what this means is we're going to, so the star bang is called the unchecked dereference pattern, and star question mark is called the checked dereference pattern. And so it's going to dereference the value that we're matching in the case of the unchecked. And in the case of the checked version, we're going to check that the value that we're matching is convertible to bool and then dereference the value. Okay, so let me give you an example here. So here's a fancy ranges min-max element where you can just pass it v, and we get out these two iterators, right? These two iterators point to the min element and the max element. So after we get the iterators out, we need to dereference them to print the values. Again, this is a single example, but we can put the star bang in front of the identifier, which will unconditionally dereference the iterator and match the result of the dereference with the pattern on the right. In this case, the pattern on the right is just an identifier, and so we're going to give be able to call them min and max rather than having to call them min iter and max iter. So save some characters. Maybe in the cases where you have to do star a whole bunch after you actually do the structured bindings, maybe it'll be helpful. But let's keep going. So suppose we have an employee class with ID and name, and we have a vector of those, and we want to call min max element on it, and we use ranges projection to compare them based on their IDs. Okay, and we're going to get the minimum employee by ID and the maximum employee by ID, right? And so we can do star bang, and as I said, because it's a pattern on the right, you can put more complex patterns there. So we're going to dereference the min iter that we had before, which will be an employee. Then we will use the structured bindings with designated initializer syntax to unpack that employee and give a good name to the name portion of that employee. And I don't care about the ID because we already did that operation. Okay, I like this example. This is an example of the star bang pattern. Let's look at what star question mark looks like. So suppose you have a simple signally linked list, and you have a node with the value and the next pointer. And we write a silly function here called starts with 2 zeros. We're going to inspect that node. We're checking that the value is 0. We're going to conditionally dereference the next pointer, right? So if the next pointer is null, then this pattern won't match at all. If the next pointer is set, then we will dereference the pointer and use the pattern value 0 to match the next node, basically. And so with this pattern, we're checking, do we have a 0, and does the next node exist? And if it exists, does it have 0? And I don't really care what happens after that. So this is how you would check. This is one way to check whether your linked list starts with 2 zeros. And the magic happens there. Right? And so note that if this was a star bang and you were the end of the list, then you would be in UB land, right? Because you would unconditionally dereference the pointer. Okay, this brings us to the last piece that I have. The extractor pattern. This is a bit complicated, so I'm going to take my time. It looks kind of similar to the dereference pattern, and it has similar semantics. But this is a way to give you customization points and customization points for introducing your own patterns. So the first form is constant expression, bang, pattern. The second one is constant expression, question mark pattern. So similar to dereference, as we just talked about, it's going to be unchecked and checked. The unchecked version matches value if we call extractor.extract value, and the pattern that we're given matches that result. Right? And so in the dereference example, the extract operation was the dereference operation. Okay? And in the checked version, we do a similar thing, except we call try extract. The thing that comes out, we're going to check whether that is implicitly convertible to bool, and that the dereferencing of that matches the pattern. So going back to the dereference example, the try extract would return something like a pointer or an optional or something like that. That thing will be implicitly convertible to bool, and the pattern will be matched against the dereference of that result. So this is a bit hard to see, but let's take a look at a concrete example. So CompilerTime regular expressions is a library by Hana, who gave a keynote recently at C++ Now, and this was a compelling example. So this is how pattern matching and regular expressions come together and stuff. So let's take a look at this example. So GTRe, if you haven't seen it, this is a basic intro example. I took this out of Hana's keynote, so I'm pretty sure it's correct. So we have an is a date function that takes a string view. We're saying CTRe match of the CompilerTime string, and we're checking that the input conforms, whether that matches the regex. And the result of that is going to be some object that is convertible to bool. And the bool tells you whether there was a match or not. There are a lot more things you can do with it, though. The first thing to note is that CTRe match is actually an object. It's not a function. And so you can actually store it. So CTRe match of the digits, letters followed by digits example can be saved into a regex pattern called ID. And then you can actually call ID.tryExtract on the input, and you get a result. Right? Now that result is implicitly convertible to bool, which tells you whether it actually matched or not. And if you dereference it, then you can unpack the results with structured bindings. And so in this example, the first piece is going to be the full match, and the second piece is going to be the digits portion that we captured with parentheses in the regex. Okay? So how does this fit with what we were looking at? We have (question_mark) pattern, right? This was the checked extractor pattern. Matches value if ID.tryExtract input equals x, and x is implicitly convertible to bool, and the pattern matches star x. Okay, so let me go back. So this was the condition. I'm going to replace e with ID and x with result, basically, right? And the corresponding patterns. And so what this means is that CTRe match is actually an extractor pattern that we can use, an extractor that we can use today, if the feature existed. But in the current specification. So this is what you can do, right? You can save the CTRe match object, and then you can put it into an inspect as an extractor pattern, and you can say ID (?). If the string that you have is an ID, then it will unpack the pieces, and you have access to those pieces, the captures from your regex. If you pass it a date, and then if the string that you have is a date, then it will match and give you the portions that you captured. And so extractors are very powerful. It gives you basically full control over patterns, introducing new patterns. And so this is an example of how that might come to fruition. Okay. So hopefully I've helped you understand the benefits of pattern matching and how it works, what it's about, and how they come together, and how it fits into the existing language. And I hope that it was helpful. Hello.
Hi, how's it going? Good talk.
Thank you.
I have just a couple questions about syntax.
Okay.
First of all, I love this idea. I've loved pattern matching ever since I first saw it in OCaml. So the feature's called matching, and the keyword is match in other languages I've seen. So I'm curious why you guys chose inspect. Is that just to avoid collisions with code that already say match?
Yeah. So in the standards committee, we have a code repository and code search that we do to see how many times an identifier is used. Match is like way beyond what the committee would consider, and so that was the issue. Inspect, I think, is still in the acceptable range, but even with that, there's discussions of like, can we just make it a switch and all that kind of stuff. So, yeah, that's the reason. Hello.
Hi, great proposal. I just wondered whether you also support pattern matching over types.
Do you mean
like in a neater syntax?
Like, you mean in the case of matching variants?
No, like actually matching just over any type, and then doing
Oh, you mean like inspect some T, and then
exactly.
matching? Yeah, okay. So we don't have that currently. There are ideas and ways I think we can do that, but we don't support that in the paper today. Yeah. Hello.
So std visit code gen makes me very, very sad. How much better do you think this will be?
I don't know. I think we could do better, but part of the issue with visit is that variant is required to support constexpr, and so I'm not sure how much visit can actually help, because I've worked with I've published blog posts on how to improve on performance of visit, and I keep running into issues with constexpr support for variant. So you may have to wait for language variant for that. Okay.
So I'm going to harp on syntax a little bit. I understand the problem of identifiers versus ID expression.
Okay.
But I feel like, having to put let in case is pretty noisy.
Okay.
I don't know, could we default to one of those? So
Yeah.
Are you required to put it in, or is it only?
No. Yeah. So I did mention that at the top level it's defaults to let.
Okay.
Yeah. And so because we think that introducing new identifiers will be the more common operation, that's the and also because it fits better with existing declaration form, the default at the top level is let.
And,
is that better?
Yeah.
Okay.
That's I'm cool with that.
Okay.
My last question is pattern matching required to be exhaustive? So in other words, if you don't cover every pattern, is that a compile time error?
Right. So we can do that in subset of the cases, like variant, but we can't do that in general, right? Obviously, because of pattern guards. And the other thing is, given the language we have, even it's just an enum, right, and it has 3 values, we can't do exhaustiveness checking on that because it's not invalid for the enum to hold other values, right? And so it gets very hairy very fast.
Got it. Thank you.
Yeah.
So first, thanks for the work. I think would be really great if we would see that in 23, for example.
Thank you.
But a few things. For example, first, I guess you use double underscore because one underscore is used for a lot of variables, right?
Yeah, mostly
names.
for libraries.
I see.
For testing libraries, they use underscore as the wildcard. But anyway, go on with your question. Sorry.
So the question is more or less I would ask you to please consider any other option, even the Unix hard. two underscores, from my point of view, just looks terrible, but it's obviously just a nit.
Yeah, I hate it too.
And then the second thing, is there this very much, for my feeling, it very much connects to having a language support for STD variant. So what many languages actually do is just allowing enums to have any value type and not only integers. Is there an effort towards this?
You're talking about Rust enums or other enums where
it's in most languages that offer pattern matching, they also offer enums that actually have parameter.
Yeah. So there is some work being done on the language level variant side of things, which would let you do stuff like that. It would be basically a discriminated union in language. Yep. Hello.
Hi. So I noticed you have a distinction between inspect statements that are statements and inspect expressions.
Yes.
And of course, C++ does not have the nice advantage that Haskell and Rust has, where all things are expressions, and so you kind of have to distinguish between the two.
Right.
What was sort of the, decision to do that versus making special syntax that kind of made everything as much an expression as much as possible, having a block be there in sort of the expression thing like it is in Rust?
So I mean, coming up with the general mechanism to turn statements into expressions will be a feat in of itself.
Fair enough.
And the other thing is that so the thing is, both of them are useful in their own right? And what I mean is, like, you could say, oh, why don't we just have the expression form, and you can have expression statements, and that's fine. But what you lose is if you were to do an inspect inside of a for loop, and in one of the cases you wanted to continue or break, with the expression only version you couldn't do that.
So what's the way to handle the case where you might have a much more complicated, you want an expression statement, but you have a much more complicated set of logic to determine what that expression is that you would want to normally break up into like multiple lines instead of just having one giant expression?
I'm not sure I followed that question.
You just have like in a lot of the expression statement examples, it ended up being like x plus y, and that's the expression. But let's say I want to call another function, get something back from that, and then compose some result in some more complicated way, but I still want to be able to have the expression at the end.
I see what you're saying. That's a good question. I think you would end up having to use lambdas.
Okay.
Yeah. Sorry.
Thank you.
Thank you. But I'll consider that for sure. Yeah. Thank you.
If the wildcard matches, is there any way to access that value in the expression?
No. Wildcard means that you don't care to bind it. And so if you want to bind it, then you need to use an identifier pattern to give it a name.
Okay. So there's no way to match like everything else and then use whatever that value is.
I mean, if you want to match anything and do nothing with it, like as a default case or something, then you could use a wildcard pattern at the end of your as a last case, which will be a fallback once none of the cases match. Is that your question? I'm not sure.
No, actually, I just realized it was a stupid question.
Okay.
I figured it out. So.
Okay.
Hey.
Hi.
First of all, I'm really looking forward to having this in C++, so thanks for working on this.
Thank you.
And I apologize in advance for asking this, but how does pattern matching integrate or combine with metaprogramming? So on the one hand, rather than matching against a constant, for instance, can I match against the result of a constant expr function? And on the other hand of the spectrum, can I generate patterns at compile time?
Okay, let me take it backwards. So generate patterns at compile time, I have no idea. Once you can generate code, maybe you can do something, but most of it should fit into the extractor abstraction. But if it doesn't, we can discuss that. The first part of that was how it interacts with context expr and metaprogramming.
Yeah, so for instance, you showed examples about matching an enum against like the color red, color green, etc.
Right.
Could I replace color red with like a function call to make color red, which is context expr and just returns color red?
Sure. Yeah, that's fine. Yeah, because that's a constant expression.
Yeah. Okay. Cool. Thanks.
Yeah.
Hi. Great talk, first of all.
Thank you.
I do have one quick question. So most things in C++, overload resolution, template specialization, always works off of best match.
Yeah.
Now, in pattern matching, I can foresee the order of, say, a guard expression being sensitive to where it lies in the pattern.
Yeah.
Is it going to work off best match, or is it going to work off?
No, it's going to be first match, and it's for a good reason. So the thing about it with the best match, the way we do best match, like with overload sets, for example, right? In order to perform best match, we need to know all the candidates. And so we end up having to actually instantiate like every possible candidate to form the overload set and then perform the scoring algorithm, right? And so imagine, and like all of that happens at compile time, so that's fine. But imagine what happens if we do that at runtime, right? Like we now have to have all the candidates, evaluate them, and then like at runtime figure out which one fits best, right? And so I think in terms of the fact that it's a runtime thing kind of prevents us from we can't afford to do best matching, I don't think.
Analogous to sort of try catch, where catch is first match.
Yes, yeah, that's true as well, yeah. Right, because the try catch example is a good one because the reason why that happens at first match is also because it's at runtime, right? Yeah.
Hey, thank you very much for a very interesting proposal. If I could ask you to go to the slide with the last example with the colors.
Last example? This one?
Like, with the types, with the dynamic cast, for example, that you had. Yeah, it was before this all.
How far?
Yeah, more. Yeah, for example, one back. Yeah, for example, this one.
Yeah.
If you have structural bindings, we actually specifically write whether we want the copy or reference by whether there is auto or auto ref there. So here, if it's an I, does it mean it's a reference or is it copy of that?
Good question. So in structured bindings, the auto on the outside, which is a reference or whatever, is for the full object. Right. The identifiers that are introduced within structured bindings are not specified whether they're just bindings. Right?
Okay, so it kind of works more like a reference than.
So let me start again. So in structured bindings, when you say auto x comma y, the auto is for the entire object, right?
Okay.
And the x and y are almost like references, kind of, right?
Okay.
Those are generally called bindings. And so I here is a binding.
Okay, so
the same way they are in structured bindings.
So I could use it to modify the value and so on and so forth if it's.
Depending on if it's in this particular example, yeah.
Okay. Yeah. And the other thing, because here with the types, how the inspect knows about all of the types from STD variant? Is it possible to use like some custom, like different version of variant, like boost variant or something like this, and this will still work?
Yeah, So there are specific customization points that you can opt into to handle other variant-like types.
Okay, thank you.
Yeah, I think we probably have to cut it here. I think I'm over a bit, right? Oh, okay, I'm over 1 minute. I'll ask your question. Oh, last question, just go.
Okay.
What is it? Is it quick?
About this, you said you support custom variant types.
Yeah.
What about custom RTTI that a lot of code base have in game industry, for example?
That's a good question. Talk to me after this.
Okay.
Yeah. Okay. Thank you.